Take a solid ball, now cut it into 5 pieces. Don't stretch them, don't add anything, don't bend them, just rotate them and slide them around in space. And when you put them back together, you don't get your ball, you get 2 balls. Each one exactly the same size as the one you started with. 1 ball became 2 out of nothing. This is not a magic trick, and it is not a mistake. It's a proven theorem called the Banach-Tarski paradox, and it has been accepted mathematics since 1924. So how on earth is that allowed? The secret starts with infinity. A few episodes ago, we filled a full hotel with infinitely many rooms by just shifting guests around. The same magic lets infinity copy itself. Take all the counting numbers, 1, 2, 3, 4, and on forever. Split them into 2 piles, the evens and the odds. Now look at the evens, 2, 4, 6. Divide each by 2, and you get 1, 2, 3, the whole set of counting numbers back, complete. Do a similar relabeling to the odds, and you get another complete copy. You started with one infinite set, and out of its 2 halves, you rebuilt it twice. Infinity doesn't conserve how much. That's the door Banach-Tarski walks through. Now here's the leap. A solid ball isn't really a finite lump of stuff. To a mathematician, it's an infinite collection of points, more points than there are counting numbers. And the 5 pieces in the paradox are nothing like the slices of an orange. Each one is an infinitely fine dust of points, scattered through the ball in an unimaginably complicated way. Because there are infinitely many points, and because of the clever ways you can rotate them, each cloud of dust can be spun and shifted to fill the space of an entire ball, 2 of them side by side from the points of 1. So why doesn't this break the conservation of volume? Here's the honest catch. Those 5 pieces don't have a volume, not 0 volume, no volume at all. They are what mathematicians call non-measurable, so strange and scattered that the very idea of how much space they take up simply doesn't apply to them. Nothing is conserved because there was never a measurable amount to conserve. And to even build these pieces, you need a controversial rule called the axiom of choice, which lets you make infinitely many arbitrary selections with no pattern at all. Some mathematicians accept it without blinking, others side-eye it precisely because it leads to things like this. So, can you do this to an orange and double your breakfast? No, and here's exactly why. A real orange is made of a finite number of atoms. You can only cut it into actual chunky pieces, each of which has a real volume. The paradox needs a perfect mathematical ball, one that is infinitely divisible, sliced into clouds you could never physically make. Banach-Tarski lives in the world of pure, continuous mathematics, not in your kitchen. Your breakfast is safe. The logic, however, is completely sound. So that's 17. The thing that broke this time was the idea that cutting and rearranging can't create something from nothing. An idea that's true for every physical object and false for a mathematical ball. Brain, 0. Math, 17. We keep finding the same lesson. The rules your intuition trusts were quietly written for a small, finite world. And math is playing a much bigger game. If you want to watch that happen 16 more times, every series is linked from the start. Subscribe, because math is still undefeated and I'm keeping score.